Greetings, everybody, and welcome to Magnetism. Just a very brief introduction, a couple things to remember. And there we go. So magnets have been known for centuries. They knew about them way back when, even when they didn't know anything else. They still knew a little bit about magnets. Not too much, because we still don't know a lot about magnets today. The Chinese and Greeks knew about the magical properties of magnets because everything back then was magic if they couldn't explain it. I'm sure the Greeks probably had some god who was the god of magnetism who made the rocks fly towards each other. But that's the Greeks and they're silly. So the ancient Greeks used a stone substance called magnetite, and they discovered that the stone always pointed in the same direction. Which direction would that be? Either north or south. So later, stones of magnetite called lodestones were used in navigation. So they started using all kinds of different magnets, like to, when they went sailing or hiking or. So along comes this guy, Bill Gilbert. He's an English physician. In 1600, he's proposed that the Earth was a magnet, and predicted that the Earth would have magnetic poles. So that's why those lodestones, that magnetite, always pointed in the same direction. They pointed towards the magnetic poles. And he was right. So magnetism is the force of attraction or repulsion of magnetic material due to the arrangement of its atoms, particularly its electrons. So everything gets all lined up, and it's either going to attract or repel stuff. So here is what the field lines look like. You can see, pick a different color for this. Pink is good. See, stuff comes out of the North Pole. That's why we have these arrows here, and travels towards the South Pole. Now you're going to be doing a lab where you're actually going to be drawing these field lines. You have a little magnet, and you get to see the lines in action. You use a little compass, and the compass always points in the direction of these field lines. So the ends of a magnet are where the magnetic effects are the strongest, and these are called the poles. And each magnet has two poles, one north and one south. Every magnet has two poles. So like repels like, just like charges, like positive charges repel other positive charges. And also like electricity, opposites attract. South attracts north, just like negative attracts positive in electricity. And the duck is very happy. Or is that a chicken? I think it's a chicken. So poles of a magnet always come in pairs. You're never going to find just one pole. They don't like to be lonely, so they always travel with a buddy. So if I cut a magnet in half, let's say I sliced it right here. Oh, I sliced it with that line too. You get two magnets. Now I'm going to have north and south and a north and south. If I cut it again, I'm going to have a north and south and a north and south. I cut this all the way down. I keep getting smaller and smaller, and I'm always going to have a north and south. If I didn't, it'd be called a monopole. And monopoles we have not discovered yet. If you're a fan of the Big Bang Theory, that's why Sheldon and his crew went up to the North Pole to try to find magnetic monopoles, but they didn't, and it turned out just to be the blender. Alright, so the region where the magnetic forces act is called the magnetic field. So all these lines represent the magnetic field. And stuff comes out of the north and travels around and goes into the south. And you'll see this in our lab. You'll see this with the little arrow compasses that I have for you. So atoms themselves have magnetic properties due to the spin of the atom's electrons. Makes sense because they, like attracts like and opposites repel. So groups of atoms join, so their magnetic fields are all going in the same direction. They all kind of line up inside the magnet. And the areas of atoms are called domains. So here's the domains of a substance. See, like, here's one domain. They're all pointing the one way. Here's another domain. They're all pointing this way. Domain that way, domain that way. That's because of the atoms, the way they line up inside of the substance. So to create a good magnet, you want all these domains to be in line. All of them are pointing this way. So this is going to be our north pole, our south pole, and we're going to get lines that travel out and then back in. So when an unmagnetized substance is placed in a magnetic field, the substance can become magnetized. Now this happens when the spinning electrons line up in the same direction. So we're saying we're taking that previous picture with all domains going this way, some going this way, some going this way, and we're putting it inside of a magnetic field. It's going to cause all the particles, all these domains, to line up in the direction of the magnetic field. So if we know that our outside magnetic field is going this way, everything inside of our object is going to line up to go in the same way. So here's an unmagnetized substance. I'll say all these little black guys are the north poles and all the little white guys are the south poles. Now unmagnetized things are pretty random. They're going this way and that. So it's not magnetic. There's no definite north and south. But when we put it in a magnetic field or make it into a magnet, all of the poles line up. We get all of our norths pointing one way and all of our souths pointing the other way. And that turns us into this giant magnet that has a definite north pole and a definite south pole. There's a couple ways to break a magnet. You can drop it. It's going to shake up all the domains. You can heat it. We know from thermodynamics, if we heat something up, all the particles and atoms start moving really fast. And that's going to mess up those domains too and unmagnetize the substance. Interestingly though, if you've ever done any work, if you ever used a screwdriver that was magnetic, how they make those magnetic is they heat them up and then they put them in a magnetic field and it aligns all the particles while it's hot because the particles are already moving really fast. And so while they're moving really fast, they get them all in a line using a magnetic field, and then they leave it in that magnetic field while it cools. And then after it cools, all the particles are lined up and you have a magnetic screwdriver. So dropping it, heating it, this causes those domains to start shaking up and they start pointing different ways again. So we said before that the Earth is a magnet. So it exerts magnetic forces and is surrounded by a magnetic field that is strongest near the north and south magnetic poles. Now, what we call the North Pole is actually the South Pole of the giant Earth magnet. And what we call the South Pole is actually the North. So all of our magnetic field lines are coming out of our South Pole, our geographic South Pole, which is our magnetic North Pole. And they travel up to, where Santa Claus lives up here. So remember that Santa Claus lives at the magnetic South Pole with the geographic North Pole, and penguins live down here in the geographic South Pole, the magnetic North Pole. So sometimes the Earth's magnetic poles flip, and this happens every 500,000 years or so, and we're due for it pretty soon. It's probably why we're getting all this global warming and stuff. Could be attributing to that. So right now, we have our north down here and our south up here. I should use a different color because that's hard to see. So we have our south. That one's even harder to see. How about this guy? There we go. South, north. Now, any day now, these things could switch, and our north will be up here, and our south will be down here. And then Santa Claus will live at the magnetic North Pole and the geographic North Pole both, and penguins will live in south and south. So we use the Earth's magnetic field to find direction. I'm sure you guys have seen a compass before. So the needle of the compass always points towards the magnetic South Pole. So you're going to have a needle in this guy. It's usually something that looks like this, and one that's red and one that's clear. So the red one is actually the north end of a magnet, and it points towards the South Pole. It's attracted towards the South Pole. But that's the South Magnetic Pole, which in our case is the North Pole. I know it's confusing. You'll be doing some problems with it, and you'll see. So compass points towards the magnetic South Pole, which is the geographic North Pole. Physics is going to be a lot easier once those poles reverse themselves. Then it'll all be north and north and south and south. So we call this direction north, because remember, opposites attract. So the sun also has a magnetic field and extends far above the sun's surface. And other planets also have these too. Now the sun, it flips its magnetic poles like once a week. Like it goes really, really fast. I think it's like something like 8 days or something, 14 days. Its north and south poles switch. It's doing it constantly. But it takes like 500,000 years for the Earth to do it. And as I said, our Earth is long overdue for that magnetic shift. So when a charged particle enters a magnetic field, an electric force is exerted on it. So if a charged particle moves at a constant angle to the magnetic field, the magnetic force acting on it will cause it to move in a spiral around the magnetic field lines. So what's that say? We have our magnetic field lines. Actually, they're coming out this way. And there's a particle that gets attracted to that magnetic field and actually loop-de-loops around that magnetic field line. Just makes all these little spirals. And we'll actually see in the next PowerPoint how we can determine like which direction they're going to go in. So I'm sure you guys have heard of solar wind before, and this is the magnetic field from the sun like slamming into us. And it's constantly hitting our magnetic field. But sometimes these particles can penetrate that field. And these particles are found to be in two large regions known as the Van Allen belts. We got the outers, which are blue, and the inners, which are red. So these particles from the sun, these photons, get trapped in these Van Allen belts. Some come through as radiation, and that's why we have cancer. But a lot of them are trapped. So if we didn't have magnetic field, we'd just get bombarded with like sun crap all the time, and we'd all have cancer. Or, we'd all be like, Fantastic Four movies and turn orange and, light on fire and stuff, which would be kind of cool, but I don't think it's ever going to happen. So the Earth's magnetic field, I said, extends far into space, and it is called the Magnetosphere. So we can see these red lines, that's the Earth's magnetic fields. And we got this solar wind coming in, and it hits our magnetic fields and kind of takes it for a ride. They have solar particles coming in, hitting our magnetic field, and the magnetic field deflects them. Some of them get through, but they're caught in the Van Allen belts. And very few actually reach the Earth. So, and these ones that do are the ones that cause like cancer and bad stuff to happen. So when magnetic particles from the sun called solar wind strike the magnetosphere, we see a phenomenon called, I'm sure you guys have definitely seen this before. It's called the Aurora Borealis, or aka the Northern Lights. So this is actually caused by the solar wind hitting our magnetosphere. When particles get excited, they emit light. And that's how we get all these beautiful colors and swirls and stuff. Now in the Northern Hemisphere, it's the Aurora Borealis, or Northern Lights. And in the Southern Hemisphere, because they have them down at the South Pole too, is the Aurora Australis, which is the Southern Lights. And that's it.